I will try to make a long story short and presenting you collaboration between a fundamental research project, or maybe rather than collaboration, I should say co-evolution, of a fundamental research project and of an industrial adventure. So, at that time we were basically doing documentation, and we were puzzled because the usual way to program robots were not at all efficient. So we tried to design the most simple robotic system that we could imagine. So we took a dustbin with a light inside. There are two blue ones.
No, the big one. The big circle one.
Oh. Okay. So a dustbin with a light illuminating the inside of the dustbin, and the robotic system was made of only one control variable. So it was a vertical axis that can turn. And the command was only the position of this axis, and the sensory system was a single photocellular cell. And we started to collect some data on this system, okay, just by having the system turn around and registering some data. And this is an histogram of the data. So you have here the angular position, and here you have the measure of the cellular of the photoelectric cell, and here you have the number of data that were registered for all of this position. So everything seems perfect, but here is the top view of the same thing, and the light was somewhere here. Okay. So when you see this, there is something very puzzling, which is that there is an obvious symmetry, revolutionary symmetry of the system, and you should find this symmetry in the data, and you don't find it. Okay? There should be a symmetry here with a peak around the position where the system is facing the light. And there should be another symmetry somewhere here at 180 degrees where you have the main reflection. And you don't have this symmetry. So we asked the question at that time, why? So the first thing we checked is that the vertical axis was really vertical, and it was. That the vertical axis was really center in the dustbin, and it was. And we verified then that there was no other lights than the one in the bin, so we put the thing under a black curtain and we obtained the same data. And then we checked that the cleaning woman did a nice job so that there were no dust in the dustbin. And so it was not that again. And so we went further, and we discovered maybe the two main reasons for this absence of symmetry. And one was that the position of this was controlled by a big industrial robotic arm, and we use only 1 degree of freedom, but we had this arm, so we used it. And there was a bug in the control system, a very small bug in the control system of this arm that was never discovered before, but we discovered it here. But the main reason, one more important reason, was that the photoelectric cell had an hysteresis. So, in fact, we were exploring degrees after degrees in this sense, and as the photoelectric cell has this kind of memory, that's the main explanation for the fact that after the peak, you have a kind of memory where the light or the measure of the light stay for a while at a very high level. Okay, this is just to show you that even with a very, very simple system, you can have a lot of complexity, and this complexity arises from the fact that your model of the system is not complete. The main problem is this incompleteness, and at that time we met with Edward T. James, who was an American physicist, and he proposed the Bayesian approach to deal with this kind of problem of incompleteness. So the principle is quite simple. You have incompleteness, so you have this discrepancy between your model and your phenomenon. And to deal with incompleteness, you can transform this incompleteness into uncertainty by using learning. So you will start from a model, a probabilistic model. You will add some experimental data, and you will produce probabilistic representation. And the more incomplete your model, the more uncertainty in your result, of course. But, well, it depends how well you can describe your model, your phenomenon, and sometimes you cannot always, or I would say, you can never describe it exactly. But what's more interesting is the next step, because you have Bayesian inference, and with very simple rules, you can do reasoning, you can do exact reasoning on probability distribution. So this step has to be compared to logic, okay? Logic is to do reasoning with exact knowledge. Here it's to do reasoning with probability distribution with some uncertainty. Okay, the next step was, okay, now we have the principle of the solution, but we would like to have an operational solution, so we need a methodology to build programs, to build models, and to implement models. So in 1994, we proposed Bayesian programming. So a Bayesian program is basically made of two parts. A description, which is a probabilistic description of your phenomenon, and some questions that you can ask to this description to solve problems. The description itself is made of two parts. The specification, which are the knowledge coming from the expert, and the identification, where the learning coming from the data is occurring. Finally, the specification is made of three parts. The choice of the relevant variables. So here I took, for instance, one of the first success stories of Bayesian techniques, one of the more obvious, which is spam detection in emails. So the variables for spam detection are the Boolean variables, one detecting if it's spam or not, and I would say several tens of thousands of variables, Boolean variables, one for each word of the dictionary, saying if a word appears or does not appear in a given email. Then the second step of the specification is to re-express the joint probability distribution on all the variables as a product of sampler distribution by making some assertion, some hypothesis of conditional independencies between variables. In the case of spam, it's a very, very strong hypothesis, which is that the apparition of any word of the dictionary is conditioned only by the fact that the email is a spam or is not, neglecting any co-occurrence of words. Okay? So it's a very strong and very wrong hypothesis, but still it's working very well to detect spam.
Any word?
Sorry?
Any word?
Yeah. and the last step of the specification is to give a parametrical form for each of. Usually what's used is Laplace succession law, which is very close to histograms. And then, in the case of spam, you do learning by asking people to split their email between spam or not spam. And then the question you answer is, given the presence of so this methodology is always the same in okay, just to give you an idea, Bayesian program, the generalization of Bayesian network. I will not go in this because it's too technical, and but you can rewrite in terms of Bayesian program most probabilistic models. You have here Kalman filters, HMM, and so on. Well, at that point, we still needed one more component, which is a programming language to express Bayesian program. So in 1995, we produced the first version of ProBT, which is an inference engine to express Bayesian program. So it's a C++ API. I will not go in these details, but it's quite direct implementation in C of what you saw just before as a Bayesian program. And this is running on most operating systems and different machines. Well, at that point, the work split in two different directions. One which is more fundamental research, I would say, and another one which is more industrial. Concerning the fundamental part, we had two European projects. One which is called another biological process and cognitive process with Bayesian inference. In fact, there is a big community which is using Bayesian models to try to explain and understand their phenomena they are observing, and especially in neuroscience. So the three questions project. Microscopic level. So, is there any proof that the central nervous system is doing Bayesian or probabilistic calculation? And I have no the answer. For sure, I have no proof. And is no. The second is there any biological plausibility of Bayesian result at microscopic level? Can we build at the level of behaviors of humans or animals nice probabilistic of example of that? And the third question is how to do artifact using Bayesian. So some progress concerning algorithms and, for instance, driving robots.
When you say possibilities, do people update their probabilities because of the organisms, because of what they learn? Is that what you mean? Just
No. I mean more than that. I mean, can we logical model that are better than the present model of, for instance, at the microscopic level of process neurons or assembly of neurons are doing, and at the whole experiment where you have illusions, so the partners of this project, I will not go through the list, but there is half people coming from life science and from computer. Should say is that BIBA was a pet project. It is a commission project, and so it's a bigger project than the original one, but the partners of the BIBA project are the core of the new, bigger project. So at the same time, we started, we discovered that there could be a lot of different applications, industrial application of Bayesian inference, and we started a company which really started in 2003 with the support of CNRS, and we won different awards for innovation, and now after 2 years of existence we are about 10 people working in this company. So there are several activities, more research and development, finance application, and industry application. I will go very fast through a few examples of this application. So in research and development, mainly we are still working to improve the inference engine, ProBT, and especially we have a version of the inference engine on parallel machine, SMMP machine, and grid of processors. So it seems to, if you have a quick look at this slide, it seems that I'm all wrong because I pick out the wrong companies, but in fact the grid is coming from HP. Concerning the financial application, one example is operational risk management for banks. So banks are gathered, the main international banks are gathered in Basel, I don't know the name in English, Basel. They want to do an evaluation, at least a rough evaluation, of the loss that can occur with this risk. And we are doing Bayesian analysis of this operational risk for one of the big French banks. The second example is stock picking. So here the problem is very simple. This website will open in January, and it does provision on the evolution of stocks, and with what we did here is that for each company you have a lot of numbers, a lot of sensors saying if the stock will go up or down. And of course all these sensors, these sensors are technical ratio, are expert evaluation, and very diverse things. And what we did is that we did a fusion of all this information to try to get a better information. And this fusion is based on learning on the past 6 months of the analysis. Okay, so the fusion is oriented and selected of what works the best for the past 6 months or 1 year and use that to do prediction.
Did you win a lot of money putting this software together?
Well, I guess we will, but not by playing in a stock exchange, because, well, you don't only need to know in what direction the stock will go. Okay, you need to know. You need to have a lot of money to make a lot of money. Okay, and that's not our case, at least at the present time.
But how does this compare with standard portfolio theory that also allows you to measure risk and returns and allows you to construct rational portfolios of stocks? And that is the standard thing that is being used today.
Yeah. Well, I will make the following answer. We did this same thing for, what's the name in English? The systematic fund management. So the systematic fund management are people that are using computer programs to make the gestion, the management of a fund. And we did that 2 years ago for another big French bank. And they married this approach with all the... And for the industry, we have some military application, but I will not talk of this. We have some automotive application, especially in the ADAS system, so automatic driver assistance system. So here you have an example of detection of moving obstacles. They are very interested by pedestrians because they would like to put automatic system to help prevent accident with pedestrians. So you have the video image, then you have an extraction of the moving part, and here you have a probabilistic map of the possible occupancy of the space in front of the car. Okay? And what's especially nice here is that you have a memory of what's going on. So when a moving target is disappearing for a while behind another pedestrian or behind a wall or behind a car, then the probability of its presence doesn't go to zero straight away. Okay? It's not because you're not observing it that it's not here anymore.
But still, on average, you will not hit people on average, right? So what I'm asking is, can the system essentially, I mean, if you had an automatic vehicle with this, I understand that that's quite an improvement, but on the other hand, you don't want, it still is probabilistic. So what if indeed that person reappears again, and you don't detect it because you already said that the probability of this person moving behind something is already fine, so you can move the car or the vehicle through. What I'm saying, this is a probabilistic reasoning.
Yeah.
But is that tolerable for things like having an automatic vehicle going through a sidewalk?
Yeah, this is not made for automatic vehicles. Okay, this is made as an assistance to the driver. Especially, pedestrian is especially important for bus drivers, because most of the accidents with buses are when they are arriving or when they are leaving from their stop, because bus drivers have some angle mort, blind spot, okay, or nearly blind spot. So they want to put on buses this kind of systems, and if the system is detecting that the driver is going to do a move which is dangerous for someone somewhere near the blind spot, then there could be an alarm given to the driver. Okay. Last example, and then I will finish. It's an example of automatic driving. Oops. I am doing some probabilistic inference for my slide. So here is an example of, this is an electrical car and of automatic driving. where the car is taking the decision of avoidance, of following the road, of following a car, and of stopping in case of emergency. And, well, what should be said is that, of course, all this is in real time for the car and also for the previous example.
But in that case, I mean, if you just had a detector that someone is coming in front, you can also have a simple instruction that stops the car. So where's the updating of the probability there?
Well, it's not only stopping, okay? It has to do several things together: to follow the road in the given direction, to avoid the car just by passing, to stop when there is a pedestrian. So there are, in fact, all this is modeled with different probabilistic model. And what's nice with probabilistic model, I would say, is that it's quite easy to build hierarchical models to take more complicated decisions from simpler models.
So you can pass another car, you can calculate very faster.
Yeah, absolutely. And we also work on preventive maintenance, so trying to predict failure before they occur. In fact, probabilistic inference is quite good for diagnosis, especially for diagnosis.